Hello, everyone. This is Dustin Cerny at FasTest, the Director of Advanced Technologies. And on the chat, we have Jake Clifton. He's our Senior Electrical Engineer and available to answer any questions you may have throughout this webinar. And today we're talking about advanced connection verification and the analog output, what you can do with that. We'll start with the connection problems, what people see, what we've seen out in the field, overview our connection verification technology, discuss the opportunity costs and the savings that we can provide manufacturers that are doing leak testing, and then get into a demo of the analog device and have it integrated into a PLC. So one of the main problems we see out in the field are homemade connections and rigging devices that provide unnatural and inconsistent sealing forces. That leads to false failures and many safety problems on production lines. And we define a false failure as a product that fails a leak test, but the product is actually leak-free. It's a pretty common problem out in the field. Connections can cause can cause a false failure. Leaks in piping and inconsistent test settings can also cause false failures, but the majority of them are due to rigging or sealing issues. A false positive, on the other hand, occurs when a sealing device masks a leak or it actually seals on itself. We've seen some instances of that, and that's probably less frequent of an issue than a false failure due to a connection or rigging device. And our standard products are great at bringing first pass yield up from, a 70% target up to upwards of 90%. But there are still opportunities for operators to incorrectly rig with our standard connection tools. And that's where our smart devices come in. They really help bring first pass yield up from 90% closer to 95% or 96% or so. The costs of connection failures or rigging failures is very high, and there are many areas that can occur. Lost production time and throughput is one of the highest we see. Excessive warranty claims, if you're masking leaks and products with leaks are getting into the field, that'll be issues that come back to haunt you later. Unnecessary troubleshooting time is a big wasted effort. If a product failed the leak test and the product's actually leak-free, someone could be checking that and trying to diagnose why it's leaking when there really isn't one. We've seen connection verification used in functional testing, mainly to prevent spills, which also can be a big safety issue in fluid power and hydraulic testing, not to mention the cleanup time that is required to clean up an oil spill if you're testing a pump or other device. In the medical world, we see products scrapped if they fail a leak test. Some may be able to be retested once, others need to be thrown out right then and there, whether it's actually the product leaking or not. So we've seen a lot of different areas where leak testing failures can cause waste in production environments. So our solution to that problem and those problems is called connection verification. We've embedded a sensor in our FE and FI devices to verify that a successful connection has been made. This has been installed multiple places throughout the U.S. and Mexico. We've seen it used anywhere from medical device manufacturers doing some component testing all the way up to tier 1 engine testing, used for some functional testing and hot run testing of engines. We have discrete and analog outputs available for this sensor, and today we're focusing on the analog. And on the right, you can kind of see a visual description of what's happening at rest. You don't get a response. If you connect it properly, you'll see a green LED light up or a signal output. And if a failed connection happens, you don't see any response. And now with the analog, there's a lot more functionality that can be had by putting those limits in the PLC environment. So this is how connection verification works. We're monitoring piston location. On the lower left, you can see an actuated connector versus a connector at rest. And the piston component is called out. And we measure that to a very, very fine resolution, almost 5/1000ths of an inch. And that allows us to calibrate limits to store what is a good connection. If you actuate the device and they fall outside of those limits, you don't get the proper response. And below we can see the discrete signal output, which is a simple on-off. And the analog actually mimics what the travel is doing. It gives you a higher voltage or as the piston moves forward. So one thing we've learned throughout testing this feature in our products here in the lab, and one of the most common complaints I've heard, when I ask a question of how do you know when your main seal is worn? It is a wear item. It's an item that does shrink a little bit and then starts to cause false failures. When I ask that question, how do you know when your main seal is worn? Most people say, well, we see a string of false failures, 5 to 10 of them in a row, and we know to change the main seal. Well, all of that testing is waste. We can provide a worn main seal alert with connection verification, and specifically the analog output version of it. In our testing, we found that when that piston reaches its maximum limit, no more force is applied to the seal, and you start to see leaks occur. And we'll see some of that functionality in the demo in a little bit. So some differences between the discrete and analog versions. These are kind of a list of benefits that you can get with the technology. In the discrete, it's very simple to set up out of the box within 30 seconds. We've got a programming tool. It can apply power to the device. It also verifies that you have a good connection. And the operators get an LED status indicator. So it's a very simple way to get up and running with connection verification. I do put cycle counting on that side. If you do integrate with a PLC, there's certainly the ability to count cycles. Now, the analog output certainly requires PLC programming. You're going to need to tie it into an interface, add some logic, and create a GUI for your operators. It also has the ability to verify a good connection. It has a programmable LED status indicator in the sense that you can apply a voltage to one of the pins and it turns the LED on. In the demo we have set up, it's used to just verify that you're in that good zone. You could use the LED to tell an operator which connector to pick up if you have multiple in your test station. With analog output, you can also sense part presence, create an automatic worn seal alert, sense under travel versus over travel, and we'll get to some of those issues in the demo. And you can also set up auto-correcting limits. So where the piston lands, that's a certain distance, and that ends up being a voltage with the analog output. And you can say that every actuation needs to land within an average of the last 20 actuations. So that can account for that seal wear over time as the connectors used in production. So what does this all mean for manufacturers and people doing leak testing out in the world? Well, it saves you a lot of time, first and foremost. Without connection verification, people may run a leak test, it'll fail a leak test, they'll have to send that product to an inspection station or just rerun the leak test at the original station, or check the connections and then rerun it. So there's a lot of time wasted diagnosing what's going on with that failed leak test. With connection verification, you immediately know the connectors or the sealing devices aren't an issue. It'll give you immediate feedback as you're trying to actuate the connector, whether it's placed correctly, whether you have the right pilot pressure, or whether the main seal is good or not. So this leads to a gain in efficiency, an improvement of first pass yield, improved test reliability, and minimizing scrap in the medical world. So now I'm going to change to our camera. 1 second. And this is the device we've set up. We've got a PLC here. We've got our connector with the analog module bolted onto it, and the test piece that's turned to a couple different dimensions, 510 on one end and 480 on the other, and we'll use that to show what you can do with this. So I'm going to enter the setup menu first to really show where you set the limits and how easy that is with the analog output. I'm going to put the 510 end in there and actuate it, and we've actually had that set up to be in the good zone. That's a good leak-free connection. Now if I bring the maximum limit down, it's going to go out of range and the light is automatically going to go off. So I just did that with a few button presses. Really allowed you to set that range quickly to where we want it. I'm going to add a little buffer in there. You always want to have a little bit of a tolerance around where is a good connection. Now if I deactuate and put on the smaller end, you can kind of see where that piston lands. It's at about 3.4 volts versus the 3.8 that is actually a good signal. We also have an advanced menu where you can set some delays. We're waiting for that signal to be good for 1 second for you to get the proper response. So now we'll get into the main home screen. This is what an operator would see in their testing. We've got an actuate button to trigger the connector to start. We've got our feedback on position with a dial over here. We've got a cycle counter. We're monitoring how many cycles this has, and a couple other screens we'll get to in a minute. So let's say I put on our 510 end and actuate this. This should be a good connection. We get our lights, and it automatically triggers the leak test to start. One of the good it's one of the great features of this is that you don't have to hit 2 different buttons to actuate your connector and then begin your leak test. That will start automatically. One more time, if I actuate it, it's in the good zone, and I get my leak test to start. Now, let's say we run into a problem. There's some new production lines that came on, and there might be, a lower pilot pressure being applied to this pneumatic device. That would actually change the sealing force, and we wouldn't want that in a leak test because you may create a leak path. There may not be enough sealing force for that test application. Another way to simulate that is really under travel. If there's not the same pilot pressure, you're going to end up in a lower zone. So I'm just going to use this smaller end of the device of our test piece to really highlight what happens in an under travel condition. If I hit actuate, it doesn't get there. And now I've got an alert to the operator to check the pilot pressure and reactuate the tool. We've got a pilot gauge there, and that's good. So I'd say, well, I need to reactuate that. And maybe the operator put the device in the wrong port or something like that. So again, if I actuate, it doesn't get where it needs to go, and immediately says check pilot pressure. So this is that instant feedback that there's something wrong with that device. Now, another situation we see a lot is the short connect. What if I do this? What if a cylinder misfires or an operator doesn't put it on all the way? I'll actuate it there. It ends up in my yellow zone, and immediately it says check for short connect, reactuate your tool. So it's a great mechanism to provide training for your operators and error-proof their operation. Again, if I make it a good connection, put it all the way on there, I should fall into the good zone and start my leak test. Now, we talked earlier a little bit about worn seal alerts. I'm going to get into my setup menu and can go in advance and turn on the WSA feature and go back to my home screen. So now, let's say I actuate this with nothing on there. That would mimic the piston traveling all the way forward. And I'll immediately get an error of check for part presence. So this is doing, telling the operator to go, do I have something in there? If the part is present, replace the main seal. Right now we don't have anything in there, so it's really just alerting the part presence. But if this tube was on there and is reaching that distance, you'd get an automatic worn seal alert and a flashing button over here, which is another symbol to change your main seal. If I put the tool test piece back on and actuate it a few times, we've programmed that alert to go off our screen. I think it's after 3 actuations of being in a good zone. And our warning light went off. Another benefit to this is that we actually have a lot of different data collection capabilities now with the tool. In here on this first screen, it's kind of a little hard to see, but we're tracking reaction time. How fast is the tool actuating? We're also watching travel. This is actually a historical average of the last 3 actuations. So this data would allow you to set up the auto-correcting feature and have this change limits on the fly to monitor what is a good zone and update that automatically. And we also have a counter over here, counting the number of cycles, just like on the main screen. And I'm going to make sure I've got something set up in here, and we've got a preventative maintenance feature in our setup, and we set it to 10 cycles. So after 10 cycles, we should get an alert. So we begin our leak test, and on our 11th cycle, we get an automatic notifications. Our seals are worn, please replace seals and notify FasTest for replacement parts. So instead of doing the automatic worn seal alert, you can do a preventative maintenance worn seal alert. If you know that your main seals last 5,000 actuations or 10,000 actuations, you can set up that counter to provide you an immediate alert at 9,500 actuations. And that'll give you plenty of time to use the rest of the seal and get a seal on order so it's replaced and avoid any downtime due to a worn main seal. So we're really excited about this technology. I hope this quick demo kind of inspired you and gave you some different ideas on what you can use the analog output for and how it's used in a setup in a production environment. It's pretty amazing to be able to pick out whether it's under-traveled and you need to check pilot pressure, or whether a part is even in there, sensing part presence. A lot of this will help make all of your leak testing a little bit more reliable and provide you data to learn and characterize these devices over time. So, in wraps, if you have any questions, my contact information is there. Our electrical engineer, Jay Clifton, is always available to help with any programming questions. You know, he's available to answer how he set up this demo device and the logic within it. We also have connection verification coming out soon for our FastMate connectors. They will be available March 26th. Later next month, and we'll definitely have some more webinars available to see how those work as well. They use a similar platform and similar technology to provide that same connection verification feature. If you do have any application requests or immediate opportunities to use this, feel free to contact fastsales@fasttestinc.com, and they will route you to your local RSM or regional sales manager. Thank you, everybody, for attending. I hope it was informative and you're getting some value out of this. If there are any other comments or suggestions, please feel free to contact me or FasTest. Thank you very much for taking the time to join today, and look forward to some more webinars in the future.